We've talked about SSDs from the point of view of storage with the internal and external interfaces. Now we're going to focus on the interplay between storage and computation. In this part, we introduce terminology and a nomenclature that makes it possible for us to reason about existing work and open issues. So when concluding the part on external interfaces, we asked whether computational storage would be a way to define external interfaces which are appropriate for database workload. So here we're asking the question, so what's the case for defining external interfaces which are well suited for database workloads? There's a functionality argument and a performance argument. So in terms of functionality, the idea is to reduce the complexity of the host software, so the database storage manager. One example is joint work between IT University of Copenhagen and Microsoft Research, where we define an SSD interface well suited for the Llama storage manager. And that new SSD interface was transactional, and so a batch interface for a group of objects written together. And with the transactional interface, we avoid the log-on-log problem. With the batch object writes, we avoid the application level mapping and the round trip. So in effect, we moved the management of the log structured data structure from the host to the SSD. And in terms of addressing, in terms of naming, so from the in the host-based log structuring with the traditional SSD, we have to map in the storage manager, so in the Llama storage manager, the logical page IDs to SSD addresses, so logical block address, and then within the SSD, there's a mapping from logical block addresses to flash addresses. With our new interface, we expose the SSD understands the notion of LPID, so the logical page ID, which is defined in the Llama storage manager. So no mapping is needed within Llama, and it's the SSD itself that maps the logical page ID into flash addresses, so physical placement in a transactional manner. So that's the functionality argument. In terms of performance, we want to streamline the I/O path. So we want to avoid duplication. We want to optimize across the layers. That's one of the things we did with the aux patch. We want to reduce the CPU load, so it's a cost argument. We want to reduce data movement, so it's an energy consumption argument. And we want to be able to leverage the throughput which is available inside the SSD as much as possible, and that's a throughput argument. So providing new SSD interfaces adapted to database workloads requires a transition from the traditional memory abstraction, so read-write interface of SSD, to a communication abstraction, basically send and receive. And this transition requires computation on the SSD side to process the messages sent by the host, some form of communication protocol, and some form of integration between the computational part which processes the messages and the actual storage part within the SSD. We identified two key dimensions to reason about the interaction of computation and SSDs within storage. So first, either an SSD is accessed as a black box using only the external interfaces, or the SSD is a white box where computation has access to internal interfaces. On the other hand, storage can expose one of the standard external interfaces, or the computational element can be used to expose a new external interface. So we've identified 4 quadrants. So we have standard SSDs where so computation is predefined within the SSD. So the SSD is exposed as a black box with a standard external interface. Eventually, possibly the host sends directives to the SSD, but nothing more. Then we have programmable SSDs where computation has access to internal interfaces. As Alberto explained in part 2, those computation can be used to define new policies in the context of a standard external interface. We also have computational SSDs where a computational element is introduced on top of an SSD exposed as a black box, so only using the external interfaces. In the SNIA terminology, this is called a computational storage processor, and this can be used to expose a new interface to the host, possibly an interface that makes it possible to offload code from the host to the computational storage processor. And finally, we have what we call a co-design SSD, where a new interface is exposed, but on top of the internal interfaces of the SSD. So possibly new policies are defined to support the new interfaces. This nomenclature allows us to classify related work and open issues. So there are decades of research on SSD internals, which are related to the notion of programmable SSD. There's a lot of research that has been going on for many years, also in our community, on near data processing, which is relevant for computational SSDs. But there are also new issues related to the programming, so how to program those computational storage devices, and how to deploy solutions based on computational storage devices at scale in the cloud or on HPC systems. And then there's this new domain of co-design SSDs, where the opportunity is to define SSDs which are tailored for the needs of database workloads. So this is a one-slide survey of computational storage. Obviously, there are longer surveys that review the state of the art and identify open issues. We cite them in the paper. Here, the point I want to make is twofold. First, most of the prototypes that have been defined in the literature are tailored for the need of a specific class of system on a given hardware platform. And so there's been a lot of work, including in the database community, for near data processing on FPGA-based system, ARM-based system, x86-based computational devices. Those research prototypes focus on a database system or data flow processing engine, possibly a machine learning platform, a given similarity search algorithm, or a scientific computation application. There are now deployments using a given type of hardware for a given functionality on public cloud. So, for example, from Alibaba or Amazon, and HPC clusters in particular at Los Alamos National Lab. What's been less researched is the development of software frameworks that could be used to program computational storage. We said a couple of examples. Willow, where SSD apps are defined and uploaded and called via RTC. So in Willow, those SSD apps cannot be composed. In this case, there's notion of pipeline of tasks. Those tasks are programmed in C++, compiled on the host, and then shipped to the computational storage device. So there's notion of offload in this case. But there's still a lot of work to be done on the definition of software frameworks for programming computational storage devices. What's new as well is that there's a very significant involvement of the storage industry in the area of computational storage. So there are standardization efforts underway to integrate computational storage into the existing storage ecosystem. SNIA has developed an architecture. The document was published in August last year, where they identify fixed and programmable computational services. So the fixed services are pipeline, database filters, data compression, data deduplication. So it's a mix of traditional storage services and database services. And there is, more interestingly, this notion of programmable service. And the idea is that you can program a computational storage device by offloading an OS image, a container, possibly a bitstream for FPGA, or BPF code. And I'll say a few more words about the role of BPF in a few slides. Most importantly, a task force has been defined to integrate computational storage into NVMe. So from what we know, this task force will define a new command set for computational storage. It's likely that this command set will be based on a load and load execute abstraction, with eBPF again having a big role. And the idea is that this command set for computational storage will be for the execution of programs on the computational storage device, and data will be transferred with existing command sets on top of existing namespaces. So here's the SNIA architecture, where they identify traditional storage components, so a storage controller on top of storage. These are the orange components. And in green, we have the computational storage processors. And we can recognize the nomenclature with computational SSDs, which are composed of basically two devices, a computational storage processor on top of a traditional SSD, then programmable SSDs that integrate computational elements within an SSD that exposes a traditional interface, and then a co-designed SSD where the computational storage processor can be used to define a new interface which is exposed to the host, on top of storage, basically with access to internal interfaces. So I mentioned the role of BPF in the context of programmable computational storage services. So BPF is originally the Berkeley packet filtering. So it's used in the Linux kernel originally for networking, increasingly for performance monitoring and also security. So BPF can be seen as a vendor-neutral instruction set architecture. So it's assembly-like bytecode. Again, there's a virtual machine supporting BPF execution within the Linux kernel. There are BPF backends for CLang and GCC, so it's possible to write C code, and those compilers are going to generate BPF bytecode. So what's the role of BPF in the context of computational storage? If we take a step back, we've said that NVMe is extensible, but if we're going to extend NVMe every time we define a new interface, so this is not sustainable. So we need some form of mechanism for the host to call computational storage services within a computational storage processor. And the idea is that BPF could be that mechanism. BPF could be a way to represent calls to computational storage services and possibly additional code for the orchestration of those calls. So, and BPF is a good match for the load, unload, execute abstraction that we've discussed in the context of the NVMe computational storage platforms. Here is my take on how computational storage could be included in the context of NVMe. So it's nothing official. It's just my view on this. So very much work in progress. So we have SSDs that expose a traditional NVMe abstraction. So admin command set and one of the NVM or DNS command set. And let's assume that there's a computational storage command set in addition, which is based on the load and load execute abstraction. So we have SSDs in green here, the host in blue, and then we have a computational storage processor here in yellow. The computational storage processor exposes both an NVM command set and administration, of course, and a computational storage command set. And it's being directly connected to two NVMe SSDs. So on the host, there's a process to, C code is being transformed into BPF bytecode using CLang. XNVMe is used, say, on top of SPDK to load BPF code onto the computational storage processor. This computational storage processor is equipped with an NVMe controller and a set of functions which access the underlying SSDs, say, through XNVMe. So we have functions F1, F2, which access storage. And these functions could expose new interfaces. So that could be F1, F2, could be a new interface exposed by the computational storage processor to the host. And basically the host can, offload a BPF code, which is basically a call to one of the functions or some pre-processing, some orchestration of those two functions F1 and F2. So on the computational storage processors, so we're using the UBPF virtual machine. So it's an open source BPF virtual machine in user space. And what needs to be done is from the NVMe controller side, is to register F1 and F2 as a registered function in the UBPF virtual machine. There's an issue in terms of allocating and reallocating memory and state management. So these are still very much open issues, but that's an overall picture of how BPF could be used for computational storage within NVMe. So what are the open issues? So there's been a lot of work on near data processing, but not so much in terms of integration of what we now call a computational storage processor and external SSD. So how to support NVMe access from the computational storage processor, how to deal with data movement across multiple devices. So CMDs, as we mentioned, could be used for peer-to-peer data transfers. On the computational storage processor, the idea is the questions are how to handle naming, so how to orchestrate multiple programs, how to isolate across multiple tenants, how to use hardware acceleration, and then there's security. So what is the attack surface, how to protect it, what kind of verifier is needed for DPF on a computational storage processor. And then there's the overall system design, what should be offloaded from the host in the context of a given workload, what services to call, how to actually program the computational storage processor, how to place data in processing, and how to deploy software and computational storage processors. So a range of issues related to programming and computational storage processors and deploying programs at scale.
For co-design SSDs, we have a half a slide survey, a single system called Insider. It's co-designed together with a file system. So as a programmer, you can program some tasks which are pipelined within the drive. It's an FPGA-based controller, which is used as a computational storage processor. So the tasks which are programmed can be pipelined, and they're represented as operations on files. So there's a custom I/O stack within the FPGA controller on top of Flash. And Insider managed the protection, the isolation, the scheduling of the offloaded programs. So it's an interesting point in the design space and an interesting reference for co-design SSDs.
With co-design SSDs, what we have is a research agenda. And the main question is how can database system experts program a co-design SSD that is tailored for their workload? This is a long-term goal. This is something that Alberto and I feel very strongly about. This raises many different questions about the abstractions for the definition of new storage interface, for the definition of new policies that are what's suited for the new interfaces. Our goal with this tutorial is to organize the terminology, organize the related work, and try and motivate as many as possible to join this research agenda. So in conclusion, so the first point is that computational storage is going to be part of the NVMe ecosystem. So this is going to be a reality that, as programmers, we will have to relate to. And there are many issues that need to be tackled about the deployment and the programming of computational storage processors at scale for a range of different data-intensive systems and applications. The issues in terms of who programs the CSPs, how, what are the target workloads and use cases, how to integrate computational storage processors with the overall system design. And then there's this research agenda around co-design SSDs. What are the appropriate abstractions to allow database systems experts to program co-design SSDs? And what we see in part 7 is that today it's possible to explore this question experimentally. So we'll talk about the tools that are available to do that.
We talked a few slides ago about standard, computational, programmable, co-designed SSDs. We want to use this part to organize these notions and blow open the design space for those devices. In this part, we focus on this design space and give hints on how to navigate it. The goal of the design space is identifying different ways of pairing applications on devices. What do we mean by pairing? We characterized applications before by the workload they generate. And we know that different devices would behave differently under a given workload. So the idea is to understand those two sides of the behavior and determine the application device compatibility. Now, we have several ways of increasing this compatibility, and this is what we're going to be discussing here. What we want to run away from is what we've been calling the grandpa pairing approach, in which it is the application's job to adapt to the device. And how does it do it? Through a notion that's been recently developed of this unwritten contract. If the application follows these hidden rules, then the device is going to behave well. And these are a few items on these rules. But the question that we're asking is, why do we need to tailor only the application side of this equation? One way to start tweaking on the device side as well is to realize that device comes in all different shapes, sizes, and flavors, and that we can make a choice of which design to use when we're addressing a given workload. There are several important axes to consider when we want to pair a device with the workload. There's one in particular that's important that we're going to discuss here is the type of cell. Arguably, this is what's going to give you the biggest difference in certain workloads. Very briefly, devices are built with cells, flash cells that can store 1, 2, 3, or 4 bits per cell, and device could even be stacked. I'm going to give you an example here of a device that actually uses single-level cells and multi-level cells, 1 or 2 bits, and here are the differences in terms of times if you're performing a write and a read in one mode or the other. Just to give you an idea, a write in SLC mode can take a little less than 500 microseconds, but a particular write on MSB mode can take more than 4 times that amount. Modern devices can implement several optimizations about mixing those cells, right? Some devices can actually use SLC cells to cache writes. So you should check what your device is doing before making this selection. Changing the device, choosing a device specifically for a workload is possible, but it is a little bit radical. So we want to add a little bit of flexibility to this pairing. So now we talk about one step further in terms of adaptability, which are devices that could be configured. We discussed that NVMe has, for instance, queue priorities and have directives, and those configuration knobs can change a little bit the behavior of the device and make it fit slightly better to an application. So this is a step further in our design space. If we move even further, there are actually actual programmable devices that could have entire subsystem tweaked or changed in terms of caching, scheduling, placement, ECC, or etc. that could be changed in a way that would adapt particularly well to a given workload. Computational devices are just as flexible as programmable, but if you think about it, is an orthogonal way of changing the device. Instead of changing the device itself, what computational devices do is they allow applications to move the workload generation to inside the device. This has a number of good performance applications, but there might still be the problem that there's a little bit of incompatibility between the workload generated and the device. There are a number of examples in the literature of works that take this approach. As Philippe mentioned before, there's an effort to standardize this kind of device using BPF, but there's still work to be done on how do we move generic computations into these devices. The last mode that we're going to discuss here are fully co-designed devices. This is really the holy grail. They borrow a little bit from computational and programmable devices. From computational devices, they borrow the fact that they try to make the device as compatible with the workload as possible. From computational devices, notice that a portion of the application is running on the device, but there's no new interface. What happens is the device can filter the workload coming in and determine that for certain pieces of data, further computation is necessary, and it can perform this computation. One example application of this device is data conversion. Imagine, for instance, that we would load a number of files, flat files, CSV files, into a table, and imagine that we program the device to do that. We write the CSV files in the device, but what the device is actually writing are the data in the table format of a given database system. If we put all the techniques together, then we're going to get something like this map. We can start by considering performing device selection to adapt to a given workload, or we can choose devices that can be configured to the workload, or we can program a device to actually tailor a workload specifically. On the other axis is we can play with the computation. We can ship part of the computation to be executed on the device. And like Philippe mentioned before, this is an area that needs a little bit more study. Now we can combine those two directions, make the device programmable, and shift computation to devices and get to co-designed devices. One of the most interesting part about the notions, abstractions, and concepts that we've been discussing is that currently it is possible to experiment and evaluate them through a number of different techniques. In this part, we go over simulation, prototyping, and development techniques, and mention the tools that are currently available to deploy them. The first method we will talk about is software simulation. The idea here is to have software that implement a cycle-accurate version of what the hardware does. The hardware in question could be anything from a flash memory to an entire SSD device or to an entire system. There are several powerful simulators available that could be modified depending on how you want to modify your hardware. Of course, depending on the level of simulation that you're using, the input workload will be different. For a full system, for instance, you're going to input some sort of SQL benchmark, and all the way down to a trace of on-file operations if you're simulating a flash memory in isolation. MQSim is an example of a simulator at the device level. It is available on GitHub, and it can be used as a standalone device or as a device in a system-wide simulator. As you can see here, it models a number of internal details of an actual SSD. It gives us access to 3 out of 4 of our internal interfaces: caching, data placement, and channel scheduling. It doesn't work with the SEC, but we could include if we wanted to. It is a full-fledged NVMe device, and it allows us to play with directives and command sets. As with any of the tools that we'll discuss here, there are pros and cons about using software simulation. The pros: first, it is software, so it is very easy to learn, and the sky is pretty much the limit of what could be modeled. But pay attention, we want to model something that's realistic, so it is interesting when we have access to the data sheet of the hardware that we're modeling. The cons are, well, it can't capture, any simulation is not going to capture aspects that are not modeled. Specifically in SSDs, it is hard to capture non-determinism in general. For instance, flash errors, flash aging, etc. Software simulation also suffers from slow execution. So you can think of a simulator as a machine that runs at a few megahertz. You won't be able to simulate very, very long workloads. The next category of tools are hardware-based prototyping platforms. We're going to talk about one specific here. It's called the OpenSSD. This is a picture of the Cosmos Plus, which is the 3rd generation of such devices. It is an actual hardware platform built around an SoC. There's an FPGA, an ARM cores in this SoC. It has sockets for flash memory, and it allows an external PCIe connection. There are 2 interesting things about this device. First of all, it is a full-fledged NVMe device compatible with your system drivers. Second, a lot of the functionality of the SSD is implemented in the firmware as C coding, which makes it more accessible. There is a 4th informal generation of these SSDs with a more powerful FPGA and a better PCIe connection that's backed by a company in Korea that is commercially available. The biggest advantage of working with hardware-based prototyping is that you get to experiment with the real flash behavior, the real and idiosyncratic behavior. There are many examples of works that use these platforms. For instance, the Graph SSD that we discussed before used the Cosmos Plus. And there's a growing community around those devices. If you decide to use them, you wouldn't be alone. On the negative side, because a number of features are implemented in software, you can't expect this device to have the best latency possible. In terms of throughput, it's a pretty decent device though. There's only one option for flash now, but I know that there's a second option being worked as we speak. And the closer you get to changing features in the flash aspect, the lower parts of the device, the harder it gets. And this is what motivates our next platform, hardware-assisted development. The idea here is still to use hardware in a full-fledged NVMe device, but we want to emulate flash. We don't want to emulate it in software, so we would get a daughter card that contains an FPGA with some memory that can behave as flash memory. And we can attach this hardware-assisted emulator to any FPGA board that has a PCIe interface, and it could be extended through FMC connectors. There are available NVMe controllers in academia with open source that we can use, and I know one effort that's ongoing about developing a flash emulator for this sort of device. And here's an example of how such a platform could be built. A carrier card, for instance, could be one of the network cards offered by a company called High-Tech Global. High-Tech Global is a pretty known company in the space of hardware prototyping. We can attach an FMC extension to this card that would actually allows us to put M.2 SSDs here. And there is another company that provides hardware prototyping platforms that's called Bitware that has the FPGA that I spoke about in the previous slide. So if we put these three pieces together, we have a hardware-assisted emulator, and we can implement any kind of flash that we want here, or any kind of mixed memory that we want on this side of the device. This kind of platform can be as fast as a memory disk, and it gives you a lot of flexibility in terms of the kind of flash or even other types of memory that you want to put in your SSD. It can also emulate potentially different channel architectures. On the negative side, the flash emulator is currently under development, but you may want to develop your own as well. And the M2 module capacity currently is very limited. This won't be a very big device. In summary, each of those three methods give you a different point in terms of development speed, the execution speed, and accuracy of the results that you're going to get. They're all more or less available, so you can start experimenting with your new SSDs as soon as you want. Would like to conclude our presentation here and leave you with 4 takeaways. Number 1, making SSD behavior a part of a database's stack is not only desirable, but is currently possible. Number 2, the changes that we're making to a device should be guided by the workload that you write and understand and control. Number 3, you have the external and internal interfaces at your disposal so you can implement higher level abstraction on internal behavior and navigate the design space the way you see fit. And lastly, there are alternative platforms to implement and evaluate your changes. With that, we conclude and open up for your questions. Thank you very much for the opportunity.